So, should we start? Good morning, everybody. Let me briefly go through what we discussed last time, which was quite a lot of different things. So first of all, we talked about sound waves, and the procedure, how we arrived there, will reappear multiple times during the lecture. We linearized the two of the hydrodynamical equations, the continuity and the Euler equation, and then converted differential operators, spatial differential operators, into algebraic factors by decomposing the quantity in question, which was the density field last time, into Fourier modes. And then, of course, we have a linear algebraic equation. Not because nature is so kind, but because we made it so. And this will reappear very many times, right? And then we will need the solution theory of linear, a small part of the solution theory of linear algebraic equations. And the sound waves and the Jeans length that we derived from there and so on were one example for that. We derived an expression for the sound speed, which is very important, and we made assumptions going there. And the assumption we made in the lecture was that we have an adiabatic sound wave. And this means that compressions or pressure fluctuations are so fast that heat exchange between locations of different density does not happen. This could be different if the sound waves are slow, and then you might have isothermal sound waves. You might have something in between. And now in the problem sheet, which is in the process of being made, you will be asked to derive the sound speed for isothermal sound waves. The result is very simple. The adiabatic index will be replaced by 1, and that's it, but it's important to see that. All right, then we studied hydrostatic equilibrium, and in particular used gas with a polytropic stratification to derive the Lane-Emden equation. And this is where I want to set in again. Now, for some reason I don't see here what you see there, so let me go up here and show you the promised, not the promised land, but the promised Jupyter notebook. This first of all repeats the Lane-Emden equation and the definitions that enter into it. So the Lane-Emden equation is an equation for the scaled density contrast rho over ρ0, or rather a power of it, and it looks perfectly harmless, right? Theta double prime plus 2 over x times theta prime, sorry. No, I don't see it here. Plus theta to the power of n equals 0. So, sorry, there should be a prime here. Okay, definitions, blah, blah. And then, if you scroll down, you find it numerically implemented. So let's have a look. The first thing that we have to do is to find the first root of the solution, right? Because that will define where the object under consideration is going to end in space. And then, once I have that, I can calculate profiles for the density, radial profiles, I mean, for the density, the pressure, the temperature, and the mass. And with the mass, I mean the mass enclosed by radius r. And now I'm normalizing everything to either quantities in the center, for the density, the pressure, and the temperature. For the mass, obviously, it wouldn't make any sense. And for the mass, I'm normalizing it to the total mass. And then you see these profiles here. It's a little bit too large, maybe. Let's do it like that. Okay. This is the radius, or the horizontal axis is the radius in units of r0, and r0 was the scale radius that you defined last time. This is not the boundary of the star. right? Because the boundary of the star will itself be a multiple of R0. Boundary of the star is at 8 here. You can change that, of course. Okay. What I did here is that I inserted an adiabatic index of 3.25. Remember what we said about these indices. You expect 4/3 you expect gamma equals 4/3 for a fully relativistic gas. Then n would be 3. So this polytropic index in the Lane-Emden equation, n would be 3. If you had a non-relativistic monatomic gas, you would expect gamma equals 5/3. Then n would be 3/2. So 3.25 is quite an awkward choice. Why did I put this in? Because then you get a solar model that looks realistic. This is something that already Otto Ohreule found. And the reason why we have to fiddle with the polytropic index is that this model is in fact a little bit too simple. Right? So we have to put part of our ignorance about details of the solar model into this polytropic index. Now, suppose you want to change that. Suppose you want to have a fully relativistic gas. Let's set the index to 3. This is really awkward. Okay. Now, let's first have a look at the profiles. Hello, miss. Here we go. So first of all, not much seems have to change. Seems have to have changed. But you see now the horizontal axis ends a little bit below 7 rather than 8. So changing the index from 3.25 to 3 already has quite a pronounced effect. Suppose now you insisted on 3/2, as you would expect for a monatomic, non-relativistic ideal gas. Okay. Where am I? Oh dear. Okay. What did I do wrong? Okay. No. Okay, suppose you do that, suddenly the radius is even smaller. This is maybe not to worry, right? However, if I set the index to 1.5, as you might expect for a reasonably solar model, and then you scroll down and you see what are now the central quantities, right? The central pressure, central temperature, and so forth. And of course, then you have to say what kind of star you would like to have, right? What total radius it is supposed to have and what total mass it is supposed to have. Okay, fine. Then you can convert all that to numbers for the center. And there you find, okay, the central density is 8 grams per cubic centimeter in the sun. Central pressure, well, this is something that I can't relate to. Central temperature, 571 electron volts. That's a really cool star. That wouldn't burn anything, not even wood. So this is clearly wrong. And as I said, already Otto Ohreule in the 1920s found that you have to set this to 3.25 approximately. And then you get reasonable numbers. Then you have a central density of about 120 grams per cubic centimeter, that's realistic. a central pressure of something, and a central temperature of about a kilo electron volt. About a kilo electron volt. That's about 10 to the 7 Kelvin. That appears to be rather hot. But you need, in order to start fusion, you need enough energy to bring two protons close enough such that the strong interaction can set in. That's about 10 to the minus 15 meters. You need mega electron volts for doing that. You have kilo electron volts available. The only reason why the sun shines is the quantum tunneling effect. And that makes the process very slow. Because fusion depends on quantum tunneling, the way how the sun uses its hydrogen content is very, very careful. It only spends its hydrogen very, very slowly. And this is why it can shine so long. Okay, maybe you have heard that it takes thousands of years for two fusion processes to occur in the sun. Quantum tunneling is one reason. The other reason is that in the fusion process of turning protons into deuterium, you have to convert one of the protons to a neutron. You need the weak interaction for that. The weak interaction makes it even slower. So that's the reason why we can live, right? The sun has been shining for 4 billion years now. Man appeared on Earth, Homo sapiens appeared on Earth about 100,000 years ago. Right? So we needed that time. And if there wasn't quantum tunneling for the fusion wouldn't happen. And if there wasn't the weak interaction involved, the sun would spend its hydrogen content much more furiously. And there wouldn't be time for life to develop complicated forms of matter. All right. So much for the Lane-Emden equation. If you find it funny, just play with it. If you now combine these results with the Fermi pressure for a degenerate electron gas, you can calculate the Chandrasekhar very easily, the Chandrasekhar mass limit for white dwarfs. You will find a problem on that. It's very, very instructive. This is what Chandrasekhar did when he was a student of 18 years. And he won the Nobel Prize for that when he was, I think, 80 years. Funny, eh? Not for Chandrasekhar. All right, so much for that. I need to announce a number of things before we move on. First of all, on November 22nd, that is Wednesday in a week, we will have to empty this lecture hall here, because the Senate of the university decided that the Schüler-Informationstag, right, the high school students' information day, is going to take precedence over everything else at the university. And that means since this room will be needed for that, we have to go away. And we have booked the large lecture hall at Philosophers Walk 12, right? Philosophenweg 12, großer Hörsaal, for the lecture. So if you come here next Wednesday and you find a completely different audience and a completely different speaker, that's the reason. But then you are at the wrong place. So the better idea is just go to Philosophers Walk first. I will try to set up streaming and video recording and so on as usual. I'm not sure I'm going to succeed. This is how it is. All right, I will announce this again because, of course, there's a tendency to forget that. Now, about the menu of today. First of all, what I said last time about vorticity, circulation, and Kelvin's circulation theorem was so short that I think I need to restart there and talk about that again. Then we will have everything together to study Bernoulli's law. You see, with hydrodynamics, since the equations are so complicated, or are generally complicated to solve, it is a very good idea to see what you can say without solving them. And Bernoulli's equation is one way of not solving the hydrodynamical equations and yet say something about hydrodynamical flows. And this is very important, right? And we will draw some really puzzling conclusions from that, which I hope you will like. And then towards the end, maybe we will get to a Hagen-Poiseuille flow, which is interesting, for example, if you want to share an iced coffee with somebody else, right, then it's always good to know the Hagen-Poiseuille law. It's not so good to talk about that in that situation, but it's good to have it in mind. Okay, this will all be from the section flows under specific circumstances, right? I want to show you several important, well, astrophysically important examples of applications of the fluid equations. That's the point. Okay. Do you have questions so far concerning the Lane-Emden equation, things, sound waves? The dissipation of sound waves? No. Okay, then I'm going to restart with vorticity. I should say I should restart talking about vorticity. I'm not going to demonstrate vorticity. All right. So first of all, we have a velocity field V. The velocity field may or may not have a curl component. If it has a curl component, we call that vorticity. Have you heard of Helmholtz theorem? Who didn't? So Helmholtz theorem says that in 3 dimensions you can decompose a vector field into 2 pieces. One is a gradient and the other one is a curl. And so you always know that there will be a gradient component, there may be a curl component of the velocity field. And now let's have a look at the vorticity. Okay, good. I'm going to use the identity like that. So vector product of velocity and vorticity is the gradient of v squared and subtracted the so-called convective derivative of the velocity field. What is that? Right? This is the gradient. We will need this later, so let me drop a word on that. It's the gradient, but projected on the direction of the velocity. So it's the rate of change in the direction of the velocity. Okay. Good. Next thing, we are going to need that the total time derivative of the velocity is the partial time derivative plus the convective derivative. And now I'm going to replace or to eliminate the convective derivative with respect to the vorticity. Okay, so that's another way of saying the same thing, right? of writing down the total time derivative of the velocity field. In that way, or this expression here, we are going to use as a starting point for deriving Bernoulli's equation, so we are going to reuse that later. Okay. Now, I'm going to use the Euler equation, saying that the total time derivative, the total velocity derivative with respect to time is minus grad p over rho minus grad phi. Without inserting viscosity terms right now. I will also return to that and then add viscosity terms to see what viscosity does to the vorticity. All these nice terms, right? Viscosity, vorticity. Later we will have barotropic and baroclinic, and so on. Okay. This is Euler. Euler ideal. Now I'm going to replace the total velocity derivative as above. So I can write this. This is the left-hand side now. Okay, and now I'm going to take another curl, just for the fun of it. So I'm going to apply now a curl to this equation, then I get the time derivative of the vorticity as a first term. And that's what I wanted to have, right? I wanted to have an evolution equation for the vorticity. But now, if I take the curl, then this term does not contribute because that is the curl of a gradient. So the next term to use is the curl of V cross omega. That doesn't make it any more pretty, but okay. Then I get minus, the curl of a gradient, nothing. So the next term to use is what I get here by applying the curl to the complete term, which is gradient P vector product with gradient rho divided by rho squared. And then again, I get the curl of a gradient, and this is nothing. So this is the evolution equation for the vorticity, and some of the terms are just gone because they are by nature gradients. Now we make the so-called barotropic assumption. And barotropic means gradient P is parallel to gradient rho. What does that mean? Suppose you have a stratification as we discussed it last time, right? A polytropic. We're using the polytropic assumption for explaining the barotropic assumption. Okay. So we take the polytropic stratification for the gas, or then we know that the pressure is just a function of the density, and then the gradient of P is proportional to the gradient of rho, and then gradient P naturally is parallel to rho, and then under the barotropic assumption this term goes away. So in other words, if the pressure gradient and the density gradient are aligned, this is 0. And then these two terms together explain how the vorticity evolves over time. That's quite interesting. Let me make a very brief detour. No, let me make this afterwards. First of all, let us assume the barotropic condition here. And then we know that dt omega minus the curl of V times omega equals 0. This is how eddies in the flow evolve. And later we will see what happens if you add viscosity. Then you will see that the vorticity decays in the diffusion process by the friction that vorticity entails. But nonetheless, now we are there. So we have this equation, and remember the assumptions, right? The assumption is, first of all, there is no viscosity, we have an ideal fluid. Second, we made the barotropic assumption that gradient P and gradient rho are aligned. But if this is the case, let us now return to the circulation. And let me now write the circulation a little bit differently than I did last time. Last time I wrote, this is a line integral along a contour C. Now I'm writing the contour C as the boundary of a domain D. just because I want to use Stokes' theorem later. Okay, this is the completely harmless definition of circulation. Right? Suppose I stand on the old bridge as last time, and I throw a rubber duck into the river, and then I'm looking at how the rubber duck moves. Right? I'm integrating its velocity field over the contour. All right, that's that. Now I want to know, so this is the circulation. Now I want to know how does that change absolutely over time. And then I will have to take two changes over time into account, namely the change of the velocity field over time and the change of the contour, because I want to make the contour swim with the flow, or like that. So, first of all, this is the total time derivative of the velocity, and let me just write this term as v times dv, right? Because if I take the time derivative, this line element will be changed by the flow, so therefore with the flow speed. So this is dv here. And then I'm going to write this as that's going to be more confusing than helpful. Okay, good. Now I want to change the first of these integrals into an integral over the complete domain. Therefore, I have to take the curl of this time derivative here. If I do that, then the left-hand side of the vorticity equation is all that remains. And therefore, I'm getting this term here. And clearly, if we make the polytropic assumption, then, the barotropic assumption, then this is 0. Okay, the next term is going to be the contour integral here of gradient v squared over 2, yes, times dl. Right, I'm using that dv is the gradient of v times dl. Then I'm writing v times the gradient as the gradient of v squared over 2. All right, this one is a contour integral over a closed contour of a gradient that has to be 0. And the other one is 0 by the circulation equation. So the whole thing is 0. This is quite a famous statement, right? It tells you if the circulation in the flow is ever 0, then it will remain so. And this means that if you arrange for a situation where there are no eddies in the flow, there won't ever be any. But clearly you know we can produce any. So why? What's going wrong? It is very important to say what the limitations of Kelvin's circulation theorem are. Right? First of all, we have made the assumption that we have to do with an ideal fluid. So viscosity, of course, can help creating eddies. And the other assumption is that we have a barotropic flow. And of course, it can be baroclinic, which means that gradient P and gradient rho are not aligned. And this, for example, is one of the main reasons for having eddies in the Earth's atmosphere, for example, so-called storms. Right? Because there, the barotropic assumption is very often violated. Then you have baroclinic conditions, and then you can drive eddies as much as you want. Let me briefly mention, and that's the detour wanted to make. So if you have a baroclinic condition, then gradient P is not aligned with gradient rho. Now let's have a look at what this means for an ideal gas. Right? So here you have P is rho kBt divided by m bar, where m bar is the mean molecular mass, right? The mean mass per particle. All right, now you see if I take the gradient of P, this is kB over m bar, T times gradient rho plus rho times gradient T. Assuming that m bar is constant over space, which doesn't need to be. Right? You could also have a chemical stratification of a fluid, for example, or a gas, in which case also the m bar might change. But let's assume that's not the case, and let us assume that we do have an isothermal condition, the same temperature everywhere. Then the flow is necessarily barotropic. If you want to have a baroclinic contribution, you need to have a temperature gradient. And this shows you that you need temperature gradients, for example, in the Earth's atmosphere to drive storms. Right? If you had no temperature gradients, then Kelvin's circulation theorem would tell you, unless somebody gives you an eddy from outside, right? For example, by stirring, you wouldn't get any. Okay? So, in my view, Kelvin's circulation theorem is particularly useful for being violated, right? Because it tells you very clearly what you have to do in order to create eddies. And then if you, for example, if you think of a situation where you just stir the water, right? In a system with a finite dimension, right? You have a boundary. Then the flow velocity at the boundary is going to be zero just by friction. But you have no friction without viscosity. Right? So this shows you that you can violate, or you need to violate, typically at least one, maybe two of these assumptions, right? Having a viscosity and having baroclinic conditions rather than barotropic conditions. All right, so much for Kelvin. Now let us return as promised to this equation here. This is the Euler equation written in a different way. Right? We have just used the identity upstairs to write the time derivative differently. By the way, do you believe this or do you want to see it? Who are the believers? Who are the disbelievers? Briefly, okay? We want to know what that is. I'm going to decompose this into components, and I want to have I want to have a look at the I component of this. This is going to be using the Levi-Civita symbol for the cross product. Okay, epsilon ijk vj, that's the first component of that. Then epsilon klm dlvm, that's the k component of that curl here. Okay, now I'm using the contraction of the two Levi-Civitas. That gives you delta IL delta Jm minus delta Im delta Jl. Vj dl Vm. So in the first term, I get Vj di Vj. That's the gradient of v squared over 2. And then minus Vj dj applied to Vi. That's V times the gradient, and then you have this identity. Did the disbelievers turn into converts? Okay, so we restart here. And we are on the way to Bernoulli's equation. Very important. So let me copy this. First of all, let me write it this way, that's also pretty. Okay, now I've copied it, nothing new happened, but now I'm going to assume that I have a stationary flow. In other words, if I look at one specific point within my flow, the velocity at that point is not going to change. That's the stationarity condition. Okay, you can extend Bernoulli's theorem also to non-stationary situation, but that's not my business right now. I'm looking at stationary conditions. And then I'm going to project the whole equation onto the direction of the flow. In other words, I'm not interested in the complete possible change here, but I'm interested in the change of all these quantities here in the direction of the flow. Right, so I'm going to multiply this equation by the velocity. I could also multiply by a unit vector into the direction of the velocity field would have the same effect. Okay, then what do I get? I get V times the gradient applied to V squared over 2. Here I get nothing, right? Because V cross omega will be perpendicular to V. And since I'm looking at a change in direction of V, that's going to go. Okay, next term will be a quantity which I call H twiddle and we'll have to explain later. And next term I get is the phi. And this must be 0. So in other words, the sum of these three quantities taken along the flow is going to be a constant. In other words, V squared over 2 plus H twiddle plus phi equals some constant, let's call it B for Bernoulli, right, without specifying which Bernoulli we mean, right, because Bernoulli has an index and the index set is quite large. Now, what is H tilde? H tilde is a quantity defined in this way. It's the integral dp over rho. If you look at its term of origin here, right, that's exactly what you need in order to return to gradient p over rho once you apply this quantity to that one here. Right, then you take the gradient of an integral function here. It's going to be the integrand at the upper boundary, and then it will be v times the gradient applied to this quantity here. What is that? This is the enthalpy per unit mass. The enthalpy per unit mass. Why is that so? I'm going to explain this because it will later be used in a way that is not the enthalpy anymore, but still very often called the enthalpy. So enthalpy. Enthalpy is the thermodynamic potential that you get from the energy, from the internal energy, if you replace the volume dependence by a pressure dependence. So you get this by a Legendre transform. Its natural variables are the entropy and the pressure, and the Legendre transform is E plus PV. Okay, the differential is given by TdS plus VdP. Under adiabatic conditions, and only then, which is also often meant but not said, TdS equals 0, so dH is VdP under adiabatic conditions. Okay. Now if you divide by the mass of the fluid, either completely or in a certain volume or so, you will get the enthalpy per unit mass. And here you will have the volume divided by the unit mass, and that's going to be the density. And therefore, the integral over that is called the enthalpy per unit mass, usually without saying what you have assumed in order to arrive there, namely the adiabatic condition here. Very often, dP over rho is also called the enthalpy per unit mass under isothermal conditions. But then the enthalpy per unit mass would be 0. So that's a clear misnomer, but okay, that's often used in that way. Okay, now let's see what that is. We know that under adiabatic conditions, we can write the stratification of the pressure with the density by the polytropic law. So, this is going to be if I may put a factor of 1 into it. Now dP is P0 gamma rho divided by rho 0 to the power of gamma minus 1 d rho over rho 0. And I'm using the polytropic law here, P equals P0 times rho over rho 0 to the power of gamma, and then take the derivative of that, pulling an exponent gamma down, and so forth. So now you see this is gamma P0 over rho 0, pulling all the constants out. Then I have an integral over x to the power of gamma minus 2 dx. Right, if I may abbreviate, x equals, no, let's do it differently, because I will later use the abbreviation alpha for it. So if alpha is rho over rho 0, then I'm remaining with this integral here, which is gamma P0 over rho 0, 1 over gamma minus 1, alpha to the power of gamma minus 1. It's going to reappear later in a very similar form. But for now, I'm going to write, this is 1 over gamma minus 1. Now, gamma P0 over rho 0, rho over rho 0 to the power of gamma. This is wrong. And now it's correct again. Right, I'm using rho divided by rho 0 to the power of gamma minus 1 as rho over rho 0 to the power of gamma, and then I have to divide out this expression. But now I can identify P0 times rho over rho 0 to the power of gamma, that's P. Then I have, once I cancel the rho 0 here, I have 1 over rho, so that's gamma P over rho, that's Cs squared divided by gamma minus 1. Right, so under adiabatic conditions, I can replace this term here, the enthalpy per unit mass in Bernoulli's equation, by a term just containing the sound speed squared. And that makes it really, really interesting. And we are going to see this in examples, but for now, let me write down Bernoulli's equation again. With this expression inserted, Cs squared over gamma minus 1 instead of H tilde. Now, by the way, what does it mean in the first place? V squared over 2 is the kinetic energy per unit mass. H tilde is the pressure volume work per unit mass that the fluid has to do. Phi, of course, is the potential energy per unit mass. So this is just one expression of energy conservation, which is no surprise, because in essence we have taken a first-time integral of the Euler equation, which is the momentum conservation equation. Right? In essence, we have taken a first integral of the Euler equation and arrived at the energy conservation equation. That's no surprise, except that now we have an exact expression for the energy contained in the flow, right? Because we have been assuming that we follow the fluid flow. So this means this expression here is constant along flow lines or is constant in the flow. And then I can derive that here. Okay, now let me have one brief look at this expression here under isothermal conditions. And then I'm going to use the equation of state for an ideal gas. So now I'm calculating this enthalpy, so-called enthalpy per unit mass for an isothermal ideal gas. And again, I'm using the equation of state for the ideal gas expressed by the density and the temperature, so that dP is kBT over m bar times d rho. And since I'm assuming isothermality, the dt does not appear. Okay, then it's easy, right? Then I just get kBT over m bar integral d rho over rho. That's going to be ln rho divided by summa rho 0, where I start the integration. And now, in the isothermal case, this is also the sound speed square, as will be left to you to prove on the next problem sheet. Okay, so under isothermal conditions, we have here this expression here for Bernoulli's equation. So this is adiabatic. And this is isothermal. Isothermal in parentheses for an ideal gas. Here we have also made the assumption of an ideal gas, but only in a very hidden way. Right? We have replaced gamma times P over rho by Cs squared. This equation is correct if the isobaric thermal expansion coefficient is 1 over T. It is so for an ideal gas, it does not have to be. Okay, so in both cases here, we have less secretly and more secretly assumed that we have to do with an ideal gas. All right, that's a nice occasion for the break. So let's restart then at 10 past 10. All right, time to move on. Now, what we are going to do for the rest of this lecture today is to play with Bernoulli's equation in one form or another. And the results will be quite interesting. Remember that this term here comes from this integral over dp over rho. Because we are going to simplify this expression very quickly now for one specific situation. Number one, it's the flow of water from a faucet. Right? You have a faucet and Wasserhahn, and the water is running from it. And the cross-section of the stream of water coming from the faucet is going to change as you go down with the flow. How does it change? Why does it change? So, okay, so you have the faucet here. Water is coming out. Now you have two options. Either you close the faucet or you have a look at the stream of water here. Now, first of all, we have a one-dimensional situation. And I'm introducing a coordinate set along the flow, along this one dimension. And I'm assuming that the end of the faucet is at height h. It doesn't matter above what. Above 0. Okay. Good. So now we have v squared over 2 plus something I don't care about plus g set, which is the potential at some height z here. That must be v0 over 2, v0 squared over 2, plus the same h will plus gh. And I'm using the same enthalpy per unit mass here because the shape of the stream of water here is also characterized by the atmospheric pressure. And that's going to be the same everywhere along the flow. So dp is going to be 0, and I can neglect on both sides the h tilde here. Okay, but this means that I get v squared is v0 squared plus 2 times g h minus z. And now you have the reason why the 0 point doesn't matter. We just need the height difference, but not the height. Okay. V0 is the velocity with which the water comes out of the flow, out of the faucet. And now we need to see what continuity tells us. Right? So far we have just used Bernoulli's equation. Now we have to take into account, in addition, the continuity equation. And for that, I'm assuming that I'm placing an infinitely thin cylindrical box perpendicular with its symmetry axis aligned with the flow around the flow. Because I need to make sense of the divergence condition that the continuity equation means, right? Continuity for a stationary flow, and so far we are studying Bernoulli's equation only in stationary situations. The continuity means this, right? The divergence of rho times v must be 0. So now I'm integrating this over a volume, and it must still be 0. Right? But if I integrate this, if I integrate this over this infinitely thin volume here, there will be no flow of water, well, by Gauss' theorem. This is going to be the surface integral over the box of rho times V. Over the volume. But the boundary here, don't know what it's called, the outside of the cylinder, right? That does not contribute because it's infinitely thin. Or I can make it as thin as I like. And then I just have the difference here of the stream inward and the stream outward. Right? The stream through the top lid and the bottom lid. And they cannot change, right? Because their difference is 0. So in other words, we know that rho VA equals constant, where A is the cross-sectional area of the stream of water. Okay, the density is going to remain the same. So we know that V times A is V0 times A0. And now you know that A is V0 over V times A0, and you know how the cross-sectional area is going to change. Right? It's going to change like the square root of the velocity. So that's going to be V0 A0 divided by root V0 squared plus 2 G H minus Z. Or if you like, that's A0 divided by 1 plus 2 G H minus Z over V0 squared, which makes the change even more obvious. Okay. If you have nothing to do over Christmas, take your handy camera and see whether that is true. Flow from a faucet. That's a simple application. Now let's move to something more like rocket science. Okay. Let's have a look at the Laval nozzle. Nozzeldüse in German, right? So maybe you have wondered sooner or later why rocket nozzles look like that. Have you ever noticed? Why? Just because they are pretty? All right. So what situation do we have now? Now we have a situation like that. So we are assuming adiabatic conditions, right? We are assuming we are constructing a rocket engine, and then there will be no time for the fluid, right, for the outstreaming gas to exchange heat with the surroundings. The gravitational, or the change in gravitational potential, is just going to be neglected, and it's going to be the change in gravitational potential across the Laval nozzle. Let's ignore that. Aha. Then what do we have? We must have V squared over 2 plus CS squared over gamma minus 1 equals V0 squared over 2 plus CS0 squared over gamma minus 1, assuming that the adiabatic index is going to be the same. Does it have to be? No. Remember what we said about the adiabatic index, right? It is Cp over Cv, and we said that's F plus 2 divided by F, where F is the number of degrees of freedom per particle. But suppose you add some fuel to our rocket engine, that's going to be dissociated the hotter it gets. And then the number of degrees of freedom is going to change along the flow. We may or may not have to take this into account, but then it turns into real rocket science, right? So for the moment, let us just assume that gamma is a constant, but be aware that you are making implicit assumptions here. For example, that all of your fuel is already dissociated at the moment when it enters here. Could be. All right, what else? We will have the continuity equation in that form. Right, because at every cross-section through our nozzle, we will have to have matter balance. Okay. As usual, let us first try and convert the first of these equations into something dimensionless. And we are going to do this by taking equation 1 divided by CS0 square. Notice I'm not dividing by CS square. That would be variable along the flow. I'm dividing by CS0 square. Then I'm going to call V divided by CS0 U. That's a dimensionless velocity now. I am going to further introduce rho divided by rho 0 equals alpha. And I'm going to use CS square equals CS0 square times alpha to the power of gamma minus 1. Do you see that? CS square we had is gamma P over rho. This is gamma P0 over rho 0 times rho over rho 0 to the power of gamma. This on its own would be P. And then I need to introduce rho 0 over rho, right? So this here, by definition, is C0 square, and the rest is alpha to the power of gamma minus 1. Okay. So these are the two abbreviations, no, the three abbreviations. No, these are the two abbreviations. This is the relation for the sound speed squared that we know, and I'm going to make the equation dimensionless by dividing it by CS0. Using all that allows me to write, instead of 1 u squared over 2 plus alpha to the power of gamma minus 1, and I'm subtracting 1 from the right-hand side. Right, so this term is already over there. Then I have equals u0 squared over 2. Okay. And now I'm going to take, that's a trick now. Now I'm going to take the differential of that equation. In other words, I wonder what it tells me about changes in these quantities. And the effect is profound, right? Because then, first of all, the right-hand side is going to go to 0. And here we are going to have the differential of alpha to the power of gamma minus 1 divided by gamma minus 1, which makes the gamma minus 1 disappear. So we have u du plus alpha to the power of, I know I should write gamma minus 2 from taking the differential. I'm going to write gamma minus 1. This I have to correct by not writing d alpha, but d alpha divided by alpha. Must be 0, right? Because u0 is a constant. So that is the differential of the first equation. That tells you if you change the velocity, if you want to change the velocity by something, you will have to change the alpha by another thing. That tells you how the density changes if you need to change the velocity. Okay, fine. Now also let us take, or let us write the continuity equation in terms of our scaled quantities, so that it reads alpha u a equals constant, some constant. And let me take the differential of that as well. That gives me 3 terms, right? Because I need to take the differential of all of them separately. But then I divide by our, right, alpha UA. The result is going to be d alpha over alpha plus du over u plus dA over A equals 0. Do you see that? If I take the differential of that, I have UA d alpha plus alpha A du plus alpha U dA equals 0. And then if I divide by alpha UA, then I'm getting the equation that is right next to it. Okay, so that allows me to throw away d alpha over alpha, which is minus du over u minus dA over A. Okay, that tells me how I need to change the density, because alpha is the scaled density, how I need to scale the density if I want to change the velocity and the cross-section of my nozzle in a certain way. Okay, good. Now I eliminate the d alpha over alpha in that way, and I'm going to re-enter here. So then I have u du plus, no, minus du over u plus dA over A. This is d alpha over alpha times alpha to the power of gamma minus 1 equals 0. Aha. Now we need something else. What is a good place for something else? I want to introduce the Mach number squared. What is the Mach number? It's the ratio of the velocity divided by the sound speed. So that would be cs squared v squared divided by cs squared. Now I'm introducing my abbreviations. So that's u squared times cs0 squared. And cs squared is cs0 squared times alpha to the power of gamma minus 1. So that is cs0 squared alpha to the power of gamma minus 1. So this is just u squared divided by alpha to the power of gamma minus 1. That's the Mach number. Isn't that interesting? Because here we have a factor of alpha to the power of gamma minus 1 divided by u. Now I have it divided by u squared. So here appears alpha to the power of gamma minus 1 divided by u squared. That's 1 over the Mach number squared. Okay, so I can write this equation as u du 1 minus 1 over Mach number squared. Now I'm here. Now I'm putting the rest on the other side. So this is alpha to the power of gamma minus 1 dA over A. This is the fundamental equation of rocket science. What does it tell you? It tells you how you have to change the cross-section of the nozzle if you want to change the velocity. Okay? Now suppose you want to make the gas faster. This is the usual goal, right? Rather than making it slower, let's try to make it faster. Okay. Suppose you have a way subsonic flow, right? Fluid is moving with rather pleasant velocities. Then the Mach number is very much smaller than 1. And the left-hand side is negative. Okay, if the Mach number is very much smaller than 1, This is very much larger than 1, and the left-hand side is negative. So in other words, if you want to accelerate the fluid, you will have to narrow the nozzle. Okay, no big surprise, right? Take a sheet of paper, roll it into a cone, blow into it. You will see that, right? You blow slowly, the gas that will come out of the tip of the cone will be fast. Now suppose you blow so hard that somewhere during the flow the Mach number rises above 1. You need to blow very hard, and you should see a doctor before you do that, but nonetheless, right? Then suddenly this factor here changes sign, and then if you want to keep accelerating the flow, you will have to widen the nozzle. Okay, and this is why these nozzles look like that, right? You try to arrange the flow such that the gas makes the sonic transition at the narrowest point, and then the shape is just there to keep accelerating the gas. Because if you accidentally hit the sonic point somewhere else, right? For example, in that area or in that range of the nozzle where it's still narrowing, you will start slowing it down again. And this is one of the many surprises that you see in hydrodynamics once you get supersonic. Right? People who constructed the first airplanes, supposed to fly at supersonic speeds, can tell you a lot. Well, they could, they did by now, but not by the airplanes. But okay. They could tell you a lot of stories about the difficulties of making planes stable at supersonic speeds. And this is a tiny little example for the unexpected things that can happen when you suddenly have a supersonic transition. Okay, that was that. Isn't that funny? I have no intuition for why this happens, right? But obviously it works. Okay, third thing. Is bonding accretion. Okay, accretion is a word often used in astrophysics. It's always used when somebody eats something else. Right? So if you have a black hole eating matter, it's called accretion on the black hole. If a star eats matter surrounding it, it's called accretion on that star. Bondi does not mean that the star eats a Bondi, no, but it's named after Hermann Bondi, who studied this for the first time. The same guy who constructed with Gould and Hoyle the Bondi-Gould-Hoyle steady-state model of the universe, which is very interesting. Nonetheless, Bondi accretion, what is it? You have a point mass, and you put it into some gas, and you let it eat. Okay, so the point mass eats the gas. It just gravitationally attracts the gas and finally does what it wants to do with it, right? Swallows it if it is a black hole, or puts it on its surface if it is a white dwarf or whatever. So Bondi accretion. And what this means is that we have a spherically symmetric situation in which matter is radially flowing, driven by gravity onto the black hole. So we are ignoring any kind of angular momentum that the surrounding matter may have as it falls onto the central mass. So again, we are going to use the adiabatic Bernoulli equation, assuming there is no heat exchange within the accreting gas. This could be wrong. So let's study them both in parallel. So we have both equations from above. V squared over 2 plus Cs squared divided by gamma minus 1. Aha, now we need the gravitational potential. We assume the mass is capital M, so the gravitational potential is going to be minus Gm over R. Aha, that's going to be a constant. So that's V0 squared over 2 plus CS0 square over gamma minus 1 minus Gm over R0. Okay, good. Let us for simplicity assume that the gas is initially at rest at infinity, so far away from the gravitating center. So then this one is gone, and this one is gone, and we can bring the other one on the other side to get v squared over 2 plus cs square minus 1 divided by gamma minus 1 minus Gm over R equals 0. Looks very similar like the lava nozzle. Okay, what do we have in the isothermal case? In the isothermal case, we have CS0 square ln rho over rho 0 on the left-hand side. And we have CS0 square ln rho 0 over rho 0 on the right-hand side. So this means that the enthalpy per unit mass on the right-hand side is 0 because we have an ln1 in it. So we have v squared over 2 plus cs0 square ln rho over rho 0 minus Gm over R equals 0. This is adiabatic. This is isothermal. Okay, what does the continuity? Yeah. Ah, sorry, I have not divided by CS0 square yet. You're right, thank you. Okay, what does the continuity equation tell us? Let us have a look again at its divergence condition, diff rho times v is 0. And now write the divergence in spherical polar coordinates. So this is 1 over r square dr rho v. R square rho v. Of course. So this means r squared rho times v is constant. So if this is constant, then if I multiply this with 4 pi, it remains constant. But now I have the complete amount of mass that is flowing through a sphere with radius r per unit time. So this is the accretion flow, right? The amount of mass accreted per unit time. And since the velocity will point inward in the case of accretion, and I want m dot to be positive, I'm writing minus m dot here. Okay. Now, what do we do? Exactly the same steps as before. First of all, we divide by cs0 squared. We insert, or we use u, the abbreviation u equals alpha divided by cs0. We further use alpha defined as rho over rho 0, exactly as before. But we will now have an expression that is Gm divided by R is cs0 squared. If I take the radius away here, what dimension does this have? Do you remember the definition of the Schwarzschild radius? Gm over c squared. This is a radius. You can see this, right? Just insert the definition or the dimensions of G, M, and so on. So this is a radius that's called the Bondi radius. If you replace CS0 by the speed of light, it's the Schwarzschild radius. It's a typical radius entering here. And so I can introduce scaled coordinates just by referring the radius to the Bondi radius. Okay, equipped with all this, I can write the first equation as u squared over 2 plus alpha to the power of gamma minus 1 minus 1. Now we have the minus 1 divided by gamma minus 1. And we have minus 1 over x equals 0, right? Because everything that remains after this procedure of the Gm over r is 1 over x. Right? Scaling everything with a Bondi radius. So this is the adiabatic case. The isothermal case looks like this, with alpha only appearing in the ln alpha term. So again, that's adiabatic, and that's isothermal. Then let's have a look at what happens with the continuity equation. If I express the radius in units of Rb, the density in units of ρ0, and the velocity in units of Cs0, then I can write this equation as 4 pi Rb squared ρ0 Cs0. Beautiful combination of constants. Times x squared alpha u. These are now the dimensionless things. Minus m equals minus m dot. Now you see this expression here has the dimension of grams per second. So if I divide this over, I get a dimensionless accretion rate. So I call this here the Bondi accretion rate, m dot b. And I use this to write x squared alpha u equals mu, and mu is the negative accretion rate divided by the Bondi accretion rate. So that is what continuity tells me. Let me write it down here. X squared alpha u equals constant equals mu, with mu being a constant, assuming that the accretion rate remains the same over time. Okay, so we have these equations to solve, and we proceed in exactly the same way as before. We take the differentials of these equations and then we see what happens. So u du plus alpha to the power of gamma minus 1 d alpha over alpha plus dx over x squared equals 0. That's the differential of the Bernoulli equation in its first form, and in its second form it's u du plus d alpha over alpha plus dx over x squared equals 0, and it is 2 divided by x, 2 dx divided by x plus d alpha divided by alpha plus du divided by u equals 0. Right? That's the differential of the continuity equation. And again, the first one tells you how do you have to change the flow speed if the density changes in that way and the radius changes in that way. And then the continuity equation allows you to eliminate one of them. Let's eliminate, again, d alpha over alpha, so that I can write the first one as u du, same thing as before, right? Plus alpha to the power of gamma minus 1. Now d alpha from below here, So that's minus u du and dx over x squared. That's going to be 0. And we can do the same things as with the Laval nozzle later. So here we have u du, d alpha, this is minus d o over u, sorry, du over u minus 2 plus 2 dx over x. Why don't you say a word? Okay. Would you accept them in this way? Okay. Again, I'm eliminating d alpha over alpha from the continuity equation. D alpha over alpha is minus 2 dx over x minus du. That's happening here. Let's briefly finish this and then conclude for today. So again, I get u du 1 minus alpha to the power of gamma minus 1 divided by u squared. So again, this is the squared Mach number. And the rest goes to the other side. This is dx over x, alpha to the power of gamma minus 1, minus 1 over x. That's the adiabatic case. And you see in the isothermal case, the sound speed always remains the same. Yeah, okay. So here I have to take 1 minus 1 over u squared. Let's ignore that for the rest of the day and say this dx over x 2 minus 1 over x in the isothermal case. Okay, now pick one of them. Compare the signs of the two sides of this equation. On the right-hand side, going inward, you can't do much, right? Because dx over x will always be negative, right? You're flowing inward. But once you reach 1 over x equals a to the power of alpha to the power of gamma minus 1, the right-hand side will become 0. Now, what does this mean? So suppose x equals alpha to the power of gamma minus 1, and sooner or later you will cross that radius. Then you have three choices. Either u is 0, then the accretion flow suddenly comes to a standstill. Or du is 0, then the velocity reaches a maximum or a minimum. Or m is 1, then you reach the sonic point. And these three possibilities you have. Same here, we fix this equation next time, but this is where we are going to continue next Monday then. I'm going to finish this here. And then we will see, okay, there's going to be a critical solution which has its sonic transition exactly at the right point. This will allow you maximal accretion. And if you change the accretion rate, either you do not get a physical solution at all, or you will have one that just reaches a maximum and then slows down again. Okay? So much for today. What I wanted to do was first of all finish the discussion of the Lane-Emden equation, discuss once more, and perhaps more understandably, Kelvin's circulation theorem, and then move on to Bernoulli's equation, because Bernoulli's equation is one integral of the Euler equation, therefore allows you to say something about fluid flows without solving the hydrodynamical equations. And we already used that to arrive at three progressively more interesting, I hope, conclusions, right? About very different situations that are all controlled by two conditions, right? Continuity and the Bernoulli equation. All right. Next time I would like to finish this, then discuss one particular example of viscous flow, and then move to shock waves, right? Which sooner or later will hit you. All right. Thank you very much.